All right, y'all. Today we are going to start a completely new topic, which is an important topic of calculus. It's basically the opposite of the derivative, and it is called the integral. So go ahead and get 6.1 notes, accumulations of change, an intro to the integral down in your notes. And we will get started right away. As you're writing the title down, I'm just going to write some things down from like our do now. To kind of get started. So in the do now, we started with a graph of velocity, of my velocity, and we called this graph v of t. V of t. And then the velocity units that we used were miles per minute. All right, so that's what we started with in the do now. To estimate the total distance traveled, we found the area. We found the area of the rectangle, of the rectangle created by v of t and the x-axis. And the x-axis from or between 2 times, from 0 to 32 minutes. Okay, that's what we did in our do now. We started with a velocity function and we found the distance. We found the distance from velocity by finding the area between the x-axis, or the area of the rectangle. Okay, now what I want you to write down is this next statement, so please write this down. This area between the curve or the function, the curve just means the function, so let me write that down. This area between the curve or the function and the x-axis is called the integral. And it looks like this. Okay, so we're going to draw a funny little symbol. It's going to be probably hard for you to draw at first, but you will get used to it, and it's kind of fun to draw. It's fun to get good at it. Okay, so here we go. Here's what the integral looks like. The integral. That's an integral symbol. And what we found the integral from 0 to 32 in the time on the x-axis. So the integral from 0 to 32, these are your x boundaries, or really it was t for our function, but it's on your x-axis. So we found the integral from 0 to 32 of the velocity function with respect to time, and we got it to equal 2 miles. This was what we found in the do now. All right, I want you to make sure that you have the sentence starting with this area between the curve, and then make sure you draw the integral symbol. You know what an integral looks like. Let's also actually note that this means with respect to time, with respect to t. Not time, it's just with whatever variable. Remember, we get dy dx. That means the dx means with respect to x, so it's a very similar thing. All right, and for integrals, you always need matching variables just like you need for derivatives. The function you're integrating needs to have a variable matching what you're integrating with respect to. Okay, cool. So let's now go ahead and define just in general, what is the integral? So I think you already wrote this down, but I need you to write it down again because we really got to know it. The definite integral is the area between a curve and the x-axis, and I need you to add on to this definition. It's the area between the curve and the x-axis from 1 x value to another. Or you can say on a given interval. On a given interval. Let's go with that. Okay, so that is the definite integral. Now, this is how we write just a generic definite integral. We say the integral from a to b of f of x with respect to x is, and then we would solve the integral. So I would make sure you know how to say this. You can say the integral of f of x from x equals a to x equals b. You could say the integral from a to b of f of x, and then with respect to x. We might want to add that. With respect to x. In this case. And that, again, is coming from here. Okay. How can we estimate the integral using a graph? This is really important. It's what we did in the do now. How can we estimate the integral using a graph? By finding the area between the curve or the function line and the x-axis. It's the definition. We're just rewriting the definition. On the given interval, or for the given interval. Okay, now let's actually do some integrals. Here we go. So here's our first example. Estimate the integral from -1 to 6 of f of x with respect to x for the graph shown below. Okay, first things first, you gotta look at your boundaries. We are going from -1 to 6. Those boundaries are x values. So -1 to 6 is where we are estimating the integral on. And then how do we find the integral? Like we've said, we find the area between the curve. Here's the curve. Area between the curve and the x-axis. Oops, there's the curve. And the x-axis on that given interval. So we need to find the area that is this area shaded in green. So let me go ahead and shade it. We're trying to find all of this area in between the curve and the x-axis. And I'm sorry, trying to be a perfectionist here, but I probably don't need to be. Okay, so how are we going to find this area? Well, right now we're really just getting a rough estimate, and the best way to do it for now is by counting these squares. So that's what we're going to do. And I'm going to go really fast when I count these because I know that it's probably going to be really boring to watch me count squares. So let's go. One way you could do it is by creating certain shapes that, here, let me do this in a different color, that kind of represent perfect shapes of the squares. So from here to here is a square, a big square. We need to know the number of little squares. So it would be 1, 2, 3, 4, 5, 5 by 1, 2, 3, 4, 5, right? So that's 25 squares right here. 25 in that big square because it was 5 wide and 5 high. And then we have, let's see, this is, we're counting just perfect ones for now. This is 1, 2, 3, 4 squares. This is also 4. 1, 2, 3, 4. Yeah. This is 3. All right, and then we have these awkward little partial squares. So let's count those now, and we're going to estimate, y'all. It's not going to be perfect. I'm going to say that this one and this one combine to make 1. So let's call that 1 square. Let's say that this one and this one also combine to make 1. And then let's just call, let's just call this I don't know, let's call this 0.8. And let's call these 0.9 and 0.9. Oops. Okay, so now we need to just add up these areas. these squares. It is really important to pay attention to units. So what do I mean by that? How much are these squares increasing by? 1 each time, because we go 1, 2, 3, 4, 5. Wait. Oh, 1, 2, 3, 4, 5, 6. So we're just like increasing by 1 each time. I'll show you another example where units kind of change pretty soon here. But for now, we don't have to worry about units. So let's go ahead and write this integral now. Every time we answer one of these questions, we're always going to start by writing what it was asking for. We need to practice writing the symbol, and we need to make sure we tell AP graders what we're finding. So the integral from -1 to 6 of f of x with respect to x is approximately, we're estimating this integral, is approximately 25, the area we're adding up, plus we have 2 4s, so I'm just going to write 4 plus 4. We have a 3. We have these ones, so that's 1 plus 1, plus 0.9. We could do, I'll show you in a second. Okay, 0.9 plus 0.9 plus 0.8. Now, I wrote all of this out just so you could see what I'm doing here. I'm just adding up all the areas, right? But we didn't have to write it all out. Like expanded like this, we could have done 25 plus 2 times 4, because there's 2 4s, plus 3 plus 2 times 1 plus 2 times 0.9 plus 0.8. All right, and what we get is approximately 41.5. It's not going to be perfect. This is what I got the last time I did it, so this might not add up, this math, but it's approximately 41.5. We can't really know for sure. All we were doing was adding up the areas of each square. And oh, y'all, the area of one square, what I was saying is the area of one square is 1 by 1, right? They're all 1 by 1. Each one of these is just width 1, height 1. So equals 1 times 1 equals 1. So that's why we just like count each square as 1. All right. Let's go ahead and move on to a different example. And it's our last example. Cool. In this figure, a car is slowing down from the velocity 60 feet per second. Estimate the distance it travels from t equals 5 to t equals 25 by finding the definite integral. Okay, before we do this example, we need to go back to our chart. Y'all, remember this chart that I taught y'all where we talk about position, velocity, acceleration. So let's go position, velocity, acceleration, and you need to write this down as a reminder. Okay, we have ways to get from position to velocity. We have ways to get from velocity to acceleration. You should know that in order to do those things, you need to take integrals. We remember, derivatives. Derivatives with respect to time. We remember to go, actually, I'll do this up top. We remember to go to the right, we have to take the derivative. Oh my gosh, y'all, I'm struggling. dt. The derivative with respect to time. Derivative with respect to time. And you know what? I'm going to make these arrows the same color as the derivative. So to travel to the right, you take the derivative. To travel to the left, you take the integral. The integral is the opposite of the derivative. So I want you to write that down and remember this means derivative, the green means derivative, and the pink means integral. So maybe, put that in your notes. This means take the integral. Why am I going over this? Well, let's look at what this question asks for. This question asks for the distance. Let me highlight that. This question wants the distance. Well, which one of these most likely has units of distance? Let's go ahead and write like some fake units. Remember how we did this? Position units. Some fake units might be meters. Actually, let's use the units that we've got in our question here. So let's see. Feet. Let's call position feet. Oops, I just wrote meters again. Velocity is feet per second. So let's write that, feet per second. Remember when you take the derivative to get velocity, you get a unit of time in the denominator? And then when you take the derivative again, you get a second unit of time in the denominator. So we have feet per second squared. Okay, so what are we trying to get to? We're trying to get to the distance. And distance units are feet. We're trying to get to the position. The distance has feet units. So what do we need to do? We're starting with velocity, and we need to go to position. We need to take an integral. To go backwards from velocity to position, you take an integral. So what do? We find the area. All right, we find the area. Let's see, it says from t equals 5 to t equals 25. So t equals 5, that's right here. T equals 25, that's right here. We need to find the area between the curve and the x-axis between these two times. That area is going to be, because it's the integral of velocity, that area is going to be the distance. It's going to be units of feet. And I'll show you why in a second. Okay, so let's really quickly do this. Let's make sure we know how many each square is. So I'm going to draw like a square over here. One square it goes by 5 here, so 5. And then it goes up by, let's see, this is 60. So 20, 40, 60, it goes up by 20. 5 by 20. So area of a square equals 5 by 20. That equals 100. Okay, so we know one square has 100 for its area. And then let's make sure we put some units on that. So this is 5. Let's see. Oh, sorry. We're not going to put units on that yet. Yeah. Actually, yeah, we do need to put units. Sorry, here, let me put the units on the 5 and the 20. That way we can see where they came from. Sorry, y'all. Okay, so 5, the units on the 5 are the x-axis units. So what are the x-axis units? You can't really see them very well. It's seconds. So 5 seconds. And then the units on the 20 are feet per second. Because it's the vertical piece. So feet per second. Okay, so why did we do this? Because you'll see something happens with the units. We have 5 seconds times 20 feet per second to find the area of this square. Well, what happens with the units? The seconds cancel, y'all. This one's in the numerator, this one's in the denominator. So the area of one square equals 100 feet. It's important to have units correct on these real-world problems. Okay, now we're ready to actually count the number of squares, and then we'll multiply by the area of each square. We'll multiply by this area. Okay, here we go. So we have 1, 2. I'm going to say this is 3. So we have the integral from 5 to 25 of the velocity function, v of t, with respect to time, is approximately, we have 3 squares plus, let's call these like 1.5. No, hold on. That's not what I did. Let's just call this one like 4. I'll call it 1.9. Or sorry, I was going to say 1 whole. And then we'll call, yeah, I think these could be 1.5. So 1.5. I'm basically saying how much square do I have. Let's call that one 0.6. All right, this is the number of squares. Now we need to multiply that number by the area of each square. So then we would do times 100. Times 100. And that would be the total area under the curve. And you get approximately, this is what I got the first time I calculated, approximately, this is 6.5, and then times 100. Make sure you know your units, feet. This is unitless because it's just the number of squares. All right, so we have approximately, this integral is approximately 680 feet. And what that means is the car traveled approximately 680 feet. That's the distance that the car traveled over the time, 5 to 25 seconds. All right, cool. That's it for today. Let's do some practice.